talk है इसमें से।
So hello everyone, a very good morning to one and all the participants also. Today we are going to start our first session of the second of CCTA 2020. So we have the professor from ISC Bangalore, S. Kasturi Rangan. So welcome sir once again in our first session of the second day, CCTA 2020. So I'm going to handing over the mic to Dr. Ravi Verma for the introduction of Professor S. Kasturi Rangan once again. Welcome sir once again. Thank you sir.
So, good morning participants. We are really thankful to you that yesterday you turned up in a very huge number. Like in 6 to 7 hours, like more than 1,600 viewers were there for yesterday's talk. So now sir is coming with his second lecture on the material and their properties for cryogenics application. So before we starting, one more time I want to introduce my mentor in the PhD, Professor Srinivasan Kasturirangan sir. Professor Srinivasan Kasturirangan sir started his career after completion of his PhD from Tata Institute of Fundamental Research, Mumbai, in the Department of Physics in 1975. Subsequently, he joined ISC Bengaluru and serving as a scientist at the Center for Cryogenics Technology. He has more than 40 years of research experience in cryogenics engineering as a scientist. During his career, he has executed several research and development and consultancy projects funded by DST, CSIR, DAE, ISRO, and other non-governmental agencies. His areas of interest are cryogenic system, cryocoolers, cryogenics instrumentation, gas sensor, cryoabsorption pump, etc. Several students have obtained their PhD and master degrees while working with him. I was also one of them. He has more than 120 publications in national and international journals. After his superannuation in 2013, he is serving as an advisor on liquid helium plant operations at the physics department. ISC as well as a consultant to a few other institutions. He is involved also as a teaching faculty at the Talent Development Center of ISC second campus at Kadapura, Chalkare, Karnataka. So without wasting any time, I would like to invite Professor Kasturi Rangan sir for the talk on the first session for the day 2. Welcome sir.
Yeah, good morning everybody. If you permit me, as I said yesterday, I will remove this mask so that I am audible to all of you. Am I clear?
Absolutely.
Are you getting the voice properly?
Yes sir, it's coming very nice sir.
Okay, thank you. Okay, I think yesterday we had a talk on the introduction to cryogenics, its fundamentals and applications. And today we are going to discuss about the materials and their properties for cryogenic applications. Okay, like yesterday, the plan of my talk is going to be something like this. See, there are a lot of materials which are used at room temperature. You take them to cryogenic temperature, there are a lot of issues. They cannot be used. Okay, so some of the issues we will see. And then, which are the suitable materials which can be used at low temperature? Which are the unsuitable materials for low temperature? This we'll segregate. And then move on to the properties of materials at cryogenic temperatures. We are aware of several properties, and main important properties are thermal expansion, mechanical properties, and transport properties. In the transport properties, we require to study specific heat, thermal conductivity, the electrical conductivity or electrical resistance, and then lastly, superconductivity. Well, the program, what is being organized is something on composites, and composites have a lot of applications also in cryogenics. And please pardon me, I am a totally new person for composites. I do not know much about composites, so please bear with me when I make the presentation of that particular portion. Okay, but I would like to introduce a little bit about composites and their use in the cryogenic applications. So at the end of that, we'll conclude this talk. Okay, let us start with the issues of materials at cryogenic temperatures. See, normally many materials are being used at room temperature, but you remember I mentioned that the properties of this material significantly changes at low temperatures. For example, we saw the rubber becoming brittle, okay, and like a glass. So when you design a cryogenic system, so you must take care of all these changes. Okay, maybe such a brittle material cannot be used for low temperatures. There are many materials which are not at all suitable for cryogenic use. So the material selection has to be done only after, maybe a literature survey, or perhaps you have to do after a direct test at cryogenic temperatures. But in some cases, the material may turn into very special materials. They can become very useful at low temperatures. For example, we have seen the example of a superconductivity. The material resistance drops to zero, followed by Meissner effect. Such a material becomes useful as a superconducting material to carry large currents and thereby make superconducting magnets, etc. Some property changes of materials make sure that they are not suitable at all. For example, if you take carbon steel, the carbon steel become brittle, and so at cryogenic temperatures, they are not useful. Some changes of these materials themselves become useful for processing the materials. For example, if you take either rubber or tough polymers, you cannot grind them at room temperature. The only method is to use a cryogenic grinding. Make sure that it is cool to liquid temperature, then you can grind them without any problems. So what we are going to do in this lecture is to look at some of the material property changes at cryogenic temperatures and their applications. Okay. Let us look at the material selection at cryogenic temperatures. Now, which are the suitable materials for cryogenic use? Let's see that first. For example, austenitic stainless steels, ASI 304, 304L, 316, 321, and then also low carbon type of steels can be used. Aluminum alloys, for example, the alloys like 6061, 6063, 1100, etc. Copper is a very useful material for low temperature, especially for heat exchangers, fabrication of heat exchangers, etc. Now, there is also oxygen-free high-conducting copper, which is called OFHC copper. Such a copper is actually used for very low temperature applications, particularly when you want to have minimal temperature gradients. Okay. And you can also use phosphorus deoxidized brass. Okay. Niobium and titanium, they are very frequently used. Titanium is a very tough material and also lightweight, so they are used. For example, niobium is used for superconducting RF systems. Niobium becomes brittle at cryogenic temperatures, but one has to design your system properly so that it doesn't become brittle. Then we can use alloys like Invar, which is a nickel iron alloy. It can be used for making washers because they have very low coefficient of thermal expansion. We are all familiar with the usage of indium. Indium is a very soft material, a soft metal, and it is used for O-rings at low temperatures. Okay, the seals are done by vacuum seals are done by using indium O-rings. Kapton and mylar, they are used as either MLI or electrical insulation. Quads, of course, we are very familiar. Actually, nicely, we can use quads for windows because you have a very good transparency for many of the experiments. Then FRPs, fiberglass reinforced plastics like G10, G11, etc., either as support tubes or actually as nested tubes, etc., can be used for low temperature. So I have given you a list of various materials which are quite suitable for cryogenics applications. Now let's look at the unsuitable materials. Martensitic stainless steels, they generally undergo a ductile to British transition when they get cooled down, so they cannot be used. Cast iron belongs to this category. Also, carbon steels, with the large quantities of carbon percentage in the steels, they become brittle at low temperatures. But people generally use carbon steels as the outer vessel of a cryogenic tank. And sometimes the pipelines are also used with carbon steel. So when they are used in that manner, care should be taken such that the brittleness at pipes does not affect the main vacuum of the vessel, because if it fails, then of course a lot of liquid evaporation will take place, and so the whole thing will be useless. Now there are rubber and many of the plastics, perspex, etc. These cannot be used for low temperatures, but there are some exceptions like KLF and UHMW, which is ultra high molecular weight polyethylene. They are used for low temperature applications. For example, these materials are used as seats in cryogenic valves. You have valves wherein you can allow the cryogenic fluid to flow. So there are valves have the seats of the cryogenic valves are used with these, prepared with these materials. Teflon is actually a very useful material. It does not crack, but yields a lot. It has a lot of thermal contraction. It is being used at low temperature. So when you use Teflon, one has to be careful where exactly you are using. Okay, let us go into the material properties at low temperatures. So first we will start with the thermal expansion. See, I will be using thermal expansion and thermal contraction. So please remember that thermal expansion takes place when a material is heated from low temperature to high temperature, and thermal contraction takes place when the material is cooled from room temperature to low temperature. So there'll be some, interchange of these terminologies. So kindly bear with me. Okay, large thermal contraction can occur when materials are cooled to cryogenic temperatures. Okay, so what does it lead to? It leads to, for example, impact on the alignment. Suppose you have aligned some windows. Okay, so if there is a thermal contraction, the alignment may not be okay. For example, including a simple transfer siphon, the inner part, if it contracts, then it goes away from the center of the tubes. So this has to be taken care. There will be development of interferences or gaps due to dissimilar materials. Okay, so when you are actually fabricating, you should make sure that by the thermal contraction, they don't open up. On the other hand, it should be the other way. It becomes closer in tolerances and causes a lot of increased strain, and sometimes it can fail. Okay, and sometimes it can also cause impact on the wiring. And what we notice is the thermal contraction is maximum in the temperature range from 300K to 77K. Of course, there is also a slight thermal contraction from 77K to 4 Kelvin, but that is comparatively small than this main value. Okay. Let us understand how the thermal expansion really takes place, or thermal contraction really takes place. Alpha is actually the thermal expansion coefficient, which is denoted as 1 by L into delta L by delta T. L is the length of the material, delta L the change in the length for a given change in temperature. Delta L by delta T refers to that. Now, thermal expansion is caused because of the following reason. Suppose you imagine a well-arranged, atomic structure Okay, for example, let's say we'll think of a metal. All the atoms are arranged very nicely. Okay, at periodic, there is a very good periodicity of the alignment of atoms. Let's consider only two atoms which are very close by. Let's look at this, for example. This is at a very low temperature. Here we are moving it further. At low temperature, the atoms do not vibrate about the mean position, or the vibration amplitude is extremely small. Then as you keep increasing the temperature, then the atoms vibrate in their mean position. Okay. But what happens is, because of the unharmonic component of the potential, the distance between the atoms keep moving out. So there is an expansion taking place. So at higher temperature, there is a large amplitude of the oscillation of the atom in its position. Also, the distance between the atoms are increased. So this is the real cause for thermal expansion in materials. Okay, let's proceed. The thermal expansion coefficient itself goes to zero at zero slope as the temperature approaches 0 Kelvin. Actually, the thermal expansion coefficient is independent of temperature at high temperature. You can see the graph on the screen, which shows you the thermal expansion coefficient is nearly constant at high temperatures. Now, for actual practical work on the cryogenic temperature range, what we need is the integral thermal contraction or integral thermal expansion coefficient is what is required. Okay, let's look at the integral thermal contraction for different materials. The delta L by L from 300K to 100K in the first column, and then delta L by L, say from 100K to 4K in the second column. So the different materials values have been chosen here. For example, stainless steel and copper, aluminum, iron, invar, brass, epoxy, and titanium, etc. What you notice is, for example, stainless steel, it has a thermal expansion coefficient of 296 into 10 to the power minus 5, yet in the range from 300K to 100K, whereas it's just as only about 35 into 10 to the minus 5 in the range from 100K to 4K. Similarly, most of the materials, you have the same behavior. Okay. Now, looking at the thermal contraction of materials, you can plot the same data in the form of a graph. So you see this graph is actually very congested. There are a lot of data which is presented here: Invar, Pyrex, unalloyed steel, nickel, contrasted, stainless steel, copper, German silver, etc., etc. But there are also a few materials like araldite, number 15, and then perspex, which is number 16. Number 17 is nylon. And then you have Teflon, number 18. You see the Teflon. Teflon has got a very large thermal contraction, what you see on screen. Okay. Non-metals are generally found to contract more than the metals. That's what you are seeing here. So as I mentioned earlier, the thermal, whenever you make a cryogenic system, you must really take care of the thermal contraction of these materials. Okay. Now, you may remember yesterday that we showed a video in our first talk relating to what is called shrink fitting. Actually, the thermal contraction becomes very useful for making a proper joining between the two dissimilar materials. For example, you can think of joining of brass with copper, or let's say aluminum with brass and things like that. Yesterday on the video, we saw an aluminum stud was inserted into a brass hole. So actually, what is the advantage of use this technique is, first of all, the material deterioration is not there. And secondly, these materials, you can integrate a cheap material along with a costly material by the shrink fitting technique. I understand the bearings are fitted into their housing by this cryogenic technique. Probably, for instance, bikes, etc. At least when we were here as a faculty, we had requests from these companies for making these arrangements. The photograph on the screen shows an example of a shrink fitting. The two components are being fitted there. Okay. Now let's move on to the mechanical properties at cryogenic temperatures. Okay. In fact, in mechanical property, we'll talk about material strength, Young's modulus, etc., or fatigue strength. Let us look at the material strength. The material strength tends to increase at low temperature as long as there is no ductile to brittle transition. Okay. So the 300K values are the ones which are typically used for our design, because what will happen is, as you make the system work at low temperature, then the performance of the system will be better. Okay. So maybe we will have all the data available up to 77K, but if you want to go to 4 Kelvin, there are limited data which is available. One has to look for these literature values, or in case you are using a new material, then it has to be tested. Okay. Now let's see the yield strength. The yield strength is of the materials increases on lowering the temperatures. Metals have higher yield strength compared to non-metals. Okay, you see on your screen, several materials yield strength has been plotted, starting with aluminum, beryllium, copper, monal, titanium. Titanium has got a pretty good yield strength. You can see that it is at very low temperature. It has a fairly good yield strength. And then we have stainless steel, number 5. And then carbon steels, okay. And then you have a nickel steels. And you look at the Teflon, for example. Teflon has a yield strength not much compared to the other materials. So it's in a very, it has some value, but it is not much compared to many other materials. So metals in general have a higher values compared to the non-metals here. Let's look at the ductility of the materials. Now, most of the materials, the ductility of a material decreases with the decreasing temperature. As you go lower in temperature, ductility reduces. The carbon steel, as you can see in number 6 in the graph, what is shown, it has a transition, ductile to brittle transition around 100K, because of which the material become brittle at low temperature. So carbon steels are not suitable for low temperature uses. So you let us look at, there are other things like aluminum, beryllium, copper, monal, and then stainless steel, nickel steel, etc. They are quite okay. But the carbon steels has a problem because it becomes from the ductile state to brittle state at low temperature. What about the fatigue strength of materials? Fatigue strength is the stress required for failure after a certain number of cycles on a given material. Okay. In general, the fatigue strength increases on decreasing the temperature, decrease of the temperature. So what you see is, for example, the fatigue strength at 10 to the power 6 cycles have been plotted in your graphs for material like aluminum, beryllium, copper, monal, titanium, and let's say stainless steel and carbon steel, etc. So you see number 5, stainless steel, has got a fatigue strength fairly high values compared to the others. Okay. Of course, most of the material has got an increase. Aluminum, of course, shows a decrease below about 150 Kelvin. Okay. Now there is a process called the cryogenic treatment, which can be used on metals. This process modifies the microstructure of materials to enhance their performance. Normally, when steels are made, you have a heat treatment. After heat treatment, the steels are left with a certain percentage of austenite, which are not fully transformed to martensite. This is known as retained austenite, or RA. The cryogenic treatment transforms the retained austenite into martensite, which is what 90% of the steel already is, which is the desirable condition. By the cryogenic treatment, the voids, imperfections in the steel structure gets eliminated. I am very glad to say that our cryogenic technology has developed the cryogenic treatment setup. In fact, uh, Professor Durgesh Nadik will be making a presentation. I hope that he will be sharing some information about it. The cryogenic treatment enables a gradual cooling of the sample from room temperature to low temperature, and then maintaining the sample at the low temperature, which is called soaking, and then warm it back to room temperature. Okay. Now, the details of the experimental setups and some studies are shown in the next few slides. So the cryogenic treatment is something like this. You start the material at room temperature, 300 K, and then gradually allow it to cool down to low temperature. Then this is the soak period, the cryogenic, maintain that cryogenic temperature, then allow it to warm up and back to the room temperature. Okay. Now, this is the experimental setup which Professor Nadik has set it up. Now you can see the actual experimental system, and here you have a schematic view. So this is a cryogenic tank which supplies liquid nitrogen to this the inside of this vessel, and where all this material which has to be cryogenically treated are placed. Nitrogen vapor at different temperatures is allowed to enter this zone, and then thereby it cools the samples, gradually cools it from room temperature to low temperature, then maintain it at a particular temperature, and then allow, if you stop your liquid nitrogen flow, then the material is warmed up back to room temperature. Well, by this cryogenic treatment, you can see the tool steels, for example, have improved their performance. Some results are shown here. For example, the wear in microns, untreated tool is about 88. Well, I don't know the units. Some units, let's say, some take some units. When you cryogenically treat it, the value goes down by 59. That means the tool is now better. So there is a performance improvement on the tool, which is almost about 33%. The frictional force in newtons again, untreated tool has got 10.5, whereas cryotreated tool has got 7.4, and the percentage improvement is about 30%. Okay, so cryogenic treatment not only improves the microstructure, it also, for example, dimensional stability is also introduced by the process of this material. Okay, ISRO has been one of the important customers for this type of cryogenic treatment. There are some pressure transducers, the diaphragms, which are cryogenically treated and then used in their systems. Okay, let's look at the transport properties. Now we said transport property, we'll start with heat capacity or specific heats. So we know the specific heat of a material or heat capacity is the change in the internal energy to the change in the temperature, or du by dt, or we can also write it as Q divided by M divided by mass into change in the temperature. In general, at cryogenic temperature, the Cp, it should be Cp here, Cp decreases rapidly with the decreasing temperatures. Okay. Okay, specific heat decreases. So how does it modify the system? So if you look at actually in the cryogenic conditions, the system's cool down will be faster as they get colder. That means as you go to lower and lower temperature, the cooling of the system will be quite fast. Okay. At cryogenic temperatures, small heat leaks, let's say, are introduced into the system, or let's say we try to apply a heat load, then it causes large temperature rise on the system because the specific heat is low. So the temperature rise will be higher for a given heat load. Okay. Where is this heat content stored in the material? They are stored in lattice vibrations and they are stored in electrons in the case of the metals. Explanation of the temperature dependent specific heat in solids is one of the important early victories for the quantum mechanics. Okay. Now, what Dulong-Petit's law tells us is that the energy is stored in a three-dimensional object. We can call it as a three-dimensional oscillator, 3D oscillator, a perfect arrangement of atoms in 3 dimensions. That's equal to 3 times nkt, okay, which is also equal to 3 into R into D. R is the gas constant, okay. K is the Boltzmann constant, N is the Avogadro number, okay. So if you calculate what is specific heat from this expression, you find specific heat is equal to 3R, 3 times the universal gas constant. Actually, it is okay for at 300 K for most of the materials, but it does not take into account of the quantum effects. So Einstein proposed a theory wherein he said the atoms are only able to vibrate in some quantized frequency. You cannot have all different frequencies, but they will have only certain special frequencies of vibration. So which means your internal energy has now to be calculated using this new formula, N plus half into HV. So what it leads to is, it leads to a temperature dependence of the specific heat. This was further modified by Debye by using the Debye theory, which says the atoms in a solid, they are not independent units. They are all coupled together. And the coupled motion of these atoms are called phonons. So these phonons can have only certain frequencies. They cannot have all different frequencies. Okay. So if this is taken care, then the Debye's theory gives you a lattice specific heat of the solids by an expression. We don't worry about the expression, where you notice only one thing, that the term theta actually refers to the Debye temperature. So this expression leads to, if you go to 300 Kelvin, put the temperature at 300 Kelvin, this gives you a value of approximately 3 times R, which is the Dulong-Petit's value. When you go to low temperature, T less than, let's say, 1/10 of the Debye temperature, then the specific heat varies as T cube. So the T cube law, so specific heat at low temperature behaves similar to the T cube values. It is proportional to T cube. So we notice one thing, specific heat decreases with the decreasing temperature. What about the electronic contribution for specific heat? Thermal energy is also stored in free electrons in the metal. Quantum theory shows that the electrons have only certain well-defined energies. For example, if you have a conduction band and valence band, some specific energies are there. Only a small fraction of the total electrons can be excited to higher states, and they participate in the specific heat. It can be shown that the electronic specific heat is equal to some constant multiplied by temperature. In other words, it varies linearly with temperature. So now we have a lattice contribution. Now we have a electronic contribution. So if you look at the specific heat in total, the specific heat total becomes C is equal to AT cube plus B into T. The contribution of the electrons becomes important only at temperatures less than 4 Kelvin. So this is how the specific heat behaves at low temperatures. There are paramagnetic materials and other special materials. They may have anomalous specific heats. That means specific heats can be randomly varying. For example, you could see some peaks, etc. But this is because of certain transitions which may be taking place in these materials. Now let's look at the specific heats of common metals. On your right hand side, you see specific heats given for stainless steel, brass, molal, and aluminum. These are some metals. And you can see the specific heat variation. At room temperature, you may have a constant value, or higher temperatures, it may nearly a Dulong-Petit's value, and gradually as it decreases, specific heat decreases with decreasing temperatures. So the materials with specific heat anomaly, they become useful as regenerator materials. Okay, let's look at that. For example, if you take material like erbium-3 nickel or holmium copper, etc., they have magnetic transitions. Okay. Now, these magnetic, you can see the specific heat is plotted here for certain materials compared to that of lead. Lead is, of course, going down, but there is no peak in the lead. Whereas if you look at the other materials, there is a peak in the specificated low temperatures. These specificates increase at low temperature because of the magnetic transitions in these materials. Well, in fact, for cryocoolers, which is one of the important workhorse in the cryogenic temperatures, these serve as regenerator materials because now the heat content can be stored in these materials because the specific is high. Okay, so cryogenic refrigerators or cryocoolers use these special materials for storage of heat content into their body. So there are a lot of applications related to that. And yesterday we saw the cryocoolers, GM cryocooler or pulse tube cryocooler, etc. These cryocoolers use some of these material at extremely low temperatures as regenerator materials. So they are able to produce very low temperatures like close to about 2.5 Kelvin and so on. Okay. Now let's move on to the thermal conductivity of solids. We know the standard expression for thermal conductivity. The thermal conductivity is given by Q is equal to minus thermal conductivity A into area of cross section of the material into dt by dx, which is the gradient of thermal conductivity across the material. Now you notice the K is actually a function of temperature. K actually significantly varies with temperature. So obviously, when you want to calculate the heat transfer, you need to consider the variation of thermal conductivity with temperature for the particular material. Okay, let us look at thermal conductivity of metals. We mentioned earlier about the specific heat. Even for thermal conductivity, energy gets transferred both by lattice vibrations and conduction electrons. For metals, there are two scattering mechanisms for the conduction electrons. We are only looking at the electron, for example. The electron, scattering, the scattering of the electrons conduction electron can happen either by the impurities. So you can think of the impurity related thing, for example, the resistivity belonging to the scattering up by impurities, which is W0 equal to beta by T. And scattering by phonons is actually proportional to T square. The thermal resistivity is proportional to T square. So the electronic thermal resistivity has the form WE is equal to alpha T square plus beta by T. Okay. Now you remember the conductance is inverse of resistivity. So therefore K being 1 by WE, you can now look at the thermal conductivity of metals by the electrons. So we are on the left side, you have this plot of WE as a function of temperature. So you can see a dotted curve completely gradually going down, which is due to the impurity scattering. And then there is a lattice scattering, which is gradually picking up and then going to the upper values. So combine these two, then you get a curve like this. Okay, it goes like this and then gradually increases. If you look at this is thermal resistivity. Now, if you look at the conductivity, it is 1 by of this value. So you can see here on the right-hand side graph, for high purity material, you can see there's a sharp rise and then goes down. And then for low purity material, the peak is actually somewhat lower. So this explains the behavior of thermal conductivity of metals as a function of temperature. Okay. There is another heat transfer mechanism by lattice vibrations and phonons. This resistance value is something like W, thermal resistance value is A by T square. But normally one neglects the phonon heat transfer in metals. So therefore, because conduction electron heat transfer dominates, so you neglect this. Okay. Now let's look at the thermal conductivity of metals of various materials. We have been given the copper, aluminum, brass, phosphor, bronze, and stainless steel, etc. And you can see the behavior of these various materials. They have a nearly constant value at room temperature and then gradually goes down. And then the plot is given in the log graph. Okay. Y-axis is the watts per meter Kelvin. X-axis is in temperature, both on logarithmic scale. Okay. Now, thermal conductivity integrals are normally considered for your making calculations, etc. Because we know very well the thermal conductivity now depends on temperature. So the heat transfer calculation, it will become rather difficult if you try to do directly. So what we do is we make use of thermal conductivity integrals. So the heat conduction can now be written like this: Q is equal to minus G into theta 2 minus theta 1. In this, theta is nothing but the thermal conductivity integral, which is 0 to Ti. Theta I is equal to integral of 0 to Ti, the thermal conductivity value multiplied by the temperature change. So this is the thermal conductivity integral term. The factor G is actually a geometrical factor, which is G is equal to 1 by, say, x1 to x2 dx divided by x. That is the material length from one position to another position. A is the area of cross section. Okay. Now we can also have the thermal conductivity integral data available for different materials. Actually, this is from Handbook of Cryogenic Engineering by Wiesen. You can see the various materials, some of the materials which we had discussed earlier. So you have the same type of things here also: aluminum, brass, stainless steel, manganese, phosphor, bronze, all these things have been plotted here. But now the units are watts per meter because it is integral K dt. Okay, this as a function of temperature. Okay. What about the thermal conductivity integrals for metals and non-metals? Non-metals also behave very similar to the metals. The thermal conductivity integral drops, okay, but the values are somewhat lower compared to those of metals. Okay, so you can see, for example, there are data for G10, okay, quartz, stainless steel, etc. Okay, nylon, some of these materials are shown here in this graph. Okay, let's move on to the electrical properties. Electrical resistivity is normally considered. We can consider the electrical resistivity of materials because the flow of current is impeded by the resistance of the material, electrical resistance of the material. Now, Ohm's law tells us that the voltage developed across a conductor, it depends on the resistance multiplied by the current flow. Okay, the resistance value R is equal to rho multiplied by L divided by A. Rho is the electrical resistivity, L is the length of the material, A is the area of cross section. Now we are concerned only about rho at this point because we will look at how exactly the rho gets varied with the temperature. Now in a metal, conduction electrons carry the current and there are basically two scattering mechanisms. We said already about this in the earlier part. The scattering of electrons by the phonons and then scattering of electrons by the impurities or defects or dislocations. Now let's look at the electrical resistivity of metals. When temperatures are of the order of, say, d by temperature, the phonon scattering dominates. In this case, resistivity is proportional to temperature. And suppose you work at temperatures which are much less than the d by temperature, then impurity scattering dominates and rho is more or less a constant because number of impurities in the system is constant. So therefore, rho remains a constant. In between the two regions, let's say temperature is of the order of d by temperature by 3, the rho is proportional to T to the power minus 5 for the case of metals. Actually, for metals with purity, especially let's say we talk about copper, for example, there is a term which is introduced called RRR, which is called the residual resistivity ratio, and which is the resistance at 300 K divided by resistance at 4.2 K. It indicates the material purity. So if, for example, if the number is very large, it means the material is quite pure. Okay. Now, electrical resistivity of copper is plotted in this graph. It is ohm meter into 10 to the power, I think it is 8, if I am not wrong, which is plotted as on the y-axis, on the x-axis is the temperature. So for different RRR values of copper, you see this is 30, 100, 300, 1000, and then 3000, etc. These are from the Handbook of Materials for Superconducting Machinery in 1974. This from this data book, we have taken this data. So you see, as you go on reducing, as you go on increasing the RRR values, the residual resistance value is very small, so the electrical resistivity completely drops. Okay. What about the other materials like platinum, for example? A metal like platinum, the resistance decreases with decreasing temperature. As we talked about copper, the resistance also becomes constant because of the impurities at low temperature. The main application for this platinum is as a resistant thermometer, a temperature sensor for cryogenic temperatures, quite useful up to about 30 Kelvin, and then fairly linear at high temperatures. So you can think of thermometers, digital thermometers based on platinum distance, using platinum distance. Okay. What about the other materials, like for example, germanium? Amorphous materials and semiconductors have very different resistivity characteristics than metals. So the resistance actually shortly goes up. See, metals resistance decreases, whereas the semiconductors and amorphous materials, the resistance increases drastically. Okay, that's what you see here. For example, germanium is shown here in the log-log scale. So the resistance gradually increases, very sharply increases at low temperatures. The resistivity of germanium is quite non-linear, you have seen here, and typically increases with decreasing temperature due to the fewer electrons in the conduction band. Now, suppose let us take an oxide-based resistor, ruthenium oxide resistor. You can see the 1000 ohm ruthenium oxide resistor, how the resistance varies at low temperature. You see, it goes to almost about 1000 ohms at room temperature to almost about 10 to the power 5 ohms at low temperature of, let's say, something like less than 0.1 Kelvin. Okay. Now, we are going to move on to the concept of superconductivity, the topic of superconductivity. We discussed this yesterday, but still I would like to show a little more detail about superconductivity in this talk, because this is one of the important properties of materials at low temperatures. Some metals and alloys, the electrical resistance decreases with temperature and finally drops to zero, unlike copper, what we discussed a little while ago. Such a material is known as superconductor. Now, this was discovered by Camelingonus in Mercury in June 9, 1911 in the University of Leiden. You can see a photograph of Camelingonus standing in his laboratory. Okay, and you can see also the data, what he could obtain on Mercury, the resistance as a function of temperature. As I mentioned yesterday, he had to conduct the experiment for several days to ensure that the value what you get is actually a genuine value. The temperature at which the change occurs, that is from a high value, suddenly the resistance drops to zero, this is known as the transition temperature. So this temperature is also known as critical temperature. So let's look at some of the conditions for superconductivity. Critical temperature is that temperature below which the material is superconducting. Above this temperature, material is normal. That is, it will have the properties of a normal conductor. In fact, not all materials are becoming superconductors. The superconductivity also is followed by the diamagnetism, and therefore they are perfect diamagnets, which means they expel all the magnetic field which is called Meissner effect. If the external applied magnetic field exceeds a critical value, then the superconductor will revert back to normal state. In other words, superconductivity will be lost. You have a table in your screen which shows different materials and their superconducting temperatures, and also the sort of fields what can be used for them, which can be produced using them. Okay. There is a third parameter. So we have talked about critical temperature, and then we talked about the critical field. Then we also now going to talk about a critical current. A third parameter in superconductivity is called the critical current. If the critical current exceeds a certain value in a superconductor, the superconductivity breaks down. This critical current is normally called as current density. It is normally expressed in terms of critical current density, or in other words, JC. So you have three parameters: critical temperature, then critical field, then critical current. Okay. So these values have to be below a certain values. All these values have to be below a certain value so that the material becomes superconductor. When the material crosses any one of these boundaries, then the material becomes normal. The material going normal is called quenching. And this is generally we see the quenches of magnets, etc. Okay. There are other type of superconductors. The superconductor is called type 2 superconductors. There are two types, type 1 and type 2. The type 2 superconductor has two critical fields, one lower critical field and upper critical field. The lower critical field is called Hc1, the upper critical field is called Hc2. Below the lower critical field or Hc1, all the magnetic flux is completely expelled from the material. Above this, but below the second critical field, which is the higher critical field, the flux can penetrate into the superconductor. In other words, we can have both normal state and superconducting state simultaneously existing in this material. Now, the flux penetration is normally called quantized magnetic fields, or called fluxons. Now, in this mixed state, as I mentioned, you have normal material and as well as superconducting material. So, if I pass a current, the current will go through the superconducting material, but it will also have a normal behavior. Now, for example, type 2 superconducting materials are mostly alloys. Niobium is one of the exceptions. It's a type 2 superconductor. The advantage of type 2 superconductor is that it will have very large upper critical fields. So they are very useful for the technology of superconductivity. I'll just show you one example here. The Large Hadron Collider LHC, niobium titanium wire, for example, it is a courtesy from L. Botura of CERN. You can see here a three-dimensional figure in which you have a temperature on one axis, the T temperature here, and on the other axis you have the magnetic field. On the vertical axis you have the critical current, and you see a shape below which superconductivity exists. When the material crosses above this curve outside, when it comes outside, material is no more superconducting. Now the JC, for example, the critical current at 5 Tesla at 4.2 Kelvin is approximately about 3000 amperes per square millimeter. Okay, the units are amperes per square millimeter. Okay, now superconductivity has now, we have a lot more boundaries, created more boundaries than what it was earlier. Now we have what are called the low and high temperature superconductors. Materials which have their critical temperature below 25 K, they are called the low TC superconductors. Generally, some of the known materials are niobium, titanium, niobium titanium, or niobium 3 tin, etc. These are materials which are used. But you see, for reaching such low temperature, you require liquid helium as a coolant. There are also oxide-based superconductors which were discovered in 1986, like ytterbium, barium, copper oxide, etc. And Bednarz and Mullers, they discovered the superconductivity in oxides materials. They have TC values much higher, somewhere close to 100 or 110 of that order. So because of which, now we can make them superconducting by using liquid nitrogen. Okay. You please remember yesterday we showed a video of ytterbium, barium, copper oxide, a superconducting material, which was just become superconductor by using liquid nitrogen. Okay. Superconductivity is also followed by Meissner effect, because of which only the magnet could float on the surface. That is the expulsion of the magnetic field by the superconductor, and the material becoming a superconductor, becoming a diamagnet. Okay. Now there are large number of applications for superconductivity. First thing is becoming a superconducting magnet. It can be for magnetic resonance imaging or NMR, tokamaks, etc. for fusion engineering. Then there are superconducting RF cavities for particle accelerators. Okay. This is one of the important areas for superconductivity applications. Tevatron, HERA, LHC, etc. Then there is other area called magnetic levitation for transportation purposes. Then superconducting quantum interference devices, which is called SQUIDs. Okay. It is useful for the medical applications. We'll see about that. When we want to make large magnets, you require large lengths of superconducting wires. So high field magnets for MRI, NMR, etc. has to be prepared using large lengths of superconducting wires. Even today, people are fabricating these magnets with low TC materials. A cross-section of the superconductor is shown here. For example, there are a large number of strands of superconductors. The superconductor is actually embedded in a copper matrix, because there will be a lot of heat dissipation because of this. So in case of a quench, it will be able to take care. And you also notice that if you take one of the strand and then you take a cross section, it will look like this. And if you look closer, you will look like this. Okay. Now, the typical low TC superconductor cable is what you have seen on these figures. Now, the superconducting magnets, you can see how they look like. People may be using many of them for their experiments, etc. For MRI imaging, we know that there are these are all vertical magnets. What you have seen here for MRI imaging, etc. You also have horizontal type magnets. These magnets use liquid helium as a coolant. Sometimes one uses liquid helium cryostats along with helium recondensation based on cryocoolers. Nowadays, there are systems which are called dry magnet systems are coming up, and they use directly cryocoolers. That is, you start with room temperature, use a cryocooler, and gradually cool the system right to the temperature at which you can convert it into a superconducting magnet. So they do not use liquid helium, and therefore such a system is called a dry magnet systems. Okay. I mentioned about the application as the superconducting RF cavities or particle accelerators, SRF cavities, is normally made of niobium. It has a vacuum inside, which is called the beam vacuum. Of course, this is separate from the insulation vacuum. And it is also surrounded, normally these cavities are surrounded by a bath of liquid helium. There are several geometries. They are designed in different geometries, but typical geometry is the elliptical shape. You can see here, they are operable at different frequency ranges from 800 megahertz to almost 3.9 gigahertz. A typical 1LC cavity of 1.3 gigahertz is shown 1 meter long, and it is what you see on the screen here. Okay. What about magnetic levitation? I don't want to play the video. Yesterday you have seen the magnetic levitation. The magnetic levitation is because of the Meissner effect. There is the magnetic field. The material becomes a diamagnet, does not allow the magnetic field to penetrate, because of which the material, the magnet, the top floats. So that means you can have a separation between the superconducting material and the normal material and a magnet, and therefore the so-called friction between the two materials is totally avoided. So this is what is called the magnetic levitation, useful for creating trains, transports, arrangements which can go very fast, extremely fast, high speeds. You can move with these type of magnets. Normally, it is not necessary to use low temperature or superconductivity for magnetic levitation. You can also use normal electromagnets. One magnet, because in like poles repel and like poles attracts. So therefore, you can also use electromagnets as well in the case of magnetic levitation. Okay. What about squids? As I mentioned, squids are nothing but superconducting quantum interference devices. There are two superconductors which are separated by an oxide layer. Due to the effects of tunneling, the Cooper pairs cross the junction, and by this process, the flux are quantized, and therefore they can generate signals. You can use them for measurement of signals, electrical signals, okay, of extremely related to extremely small magnetic fields. That is, you can have the flux quantum, and therefore you will be able to measure the electrical signals. Uh, the medical area is called a magnetoencephalography, which monitors the signals from the brain. The low TC squids normally operate at 4.2 Kelvin, that require liquid helium, whereas high TC squids operate at liquid nitrogen temperatures. You can see in the figure in front of you, a photo in front of you, the lady is having a helmet which contains the large number of squids which monitor the brain signals. Okay. Actually, I understand that Nimhans in Bangalore, along with IGCAR Kalpakkam, they have been developing these type of squid-based systems for measurement of the brain signals, and they have many projects, ongoing projects on this. Now I touch upon the composites in cryogenics. Kindly bear with me. I am not an expert in composites, so I would like to spend a little time on just explaining to you about composites by a small video, which I will show right now.
Composites are made up of at least two distinct intended materials, which together improve product performance and/or lower manufacturing costs. Many materials routinely designated by other terms are also considered composites, including plated, clad, or coated metals. The term composite, however, has come to mean a material consisting of a matrix or base material and a reinforcement material. The matrix functions as a binder for the reinforcement and controls the physical shape and dimensions of the part. The primary purpose of the matrix is to transfer the load or stress applied to the composite to the reinforcement. The matrix also protects the reinforcement from adverse environmental effects. The reinforcement's function is to improve the mechanical properties of the composite and is typically the main load-bearing element. Reinforcement is usually in the form of fibers or particles. There are numerous methods of producing parts from fiber-reinforced thermoset polymers, with the primary types being manual layup, automated layup, spray up, filament winding, pultrusion, and resin transfer molding. Manual layup is a widely used method of manufacturing a wide range of composite parts and components. The process begins with cutting the reinforcement material to size. This may be performed using knives, scissors, disc cutters, power shears, rotary power cutters, saws, or lasers. A mold having the desired part shape is then coated with a release agent to permit subsequent part release. Composite manufacturing molds are commonly made of steel, aluminum, nickel, copper, or polymer matrix composites. Once coated with a release agent, a layer of resin called a gel coat may be applied to the mold and allowed to cure to a tacky state. As the gel coat cures, the reinforcement material is prepared for application by impregnation with wet resin or matrix material. The impregnated reinforcement material is then placed on the coated mold surface and hand-rolled for uniform distribution and removal of entrapped air. More reinforcement material and resin are applied as needed in this manner until required part thickness has been built up. This so-called wet layup method can be used with nearly all reinforcement materials and is widely used to produce glass-reinforced polyester products and sometimes glass-reinforced epoxy products. Wet layup is also used for making composite molds. Layup can also be performed using prepreg material. Use of prepreg eliminates separate handling of the reinforcement and resin. Prepreg reduces resin consumption and can improve part quality by providing more consistent control of reinforcement and resin contents. However, prepreg must be kept in refrigerated storage until use time to prevent pre-curing. Composites are made up of at least two distinct intended materials: a matrix or base material.
I think we'll move back to our presentation. We have heard something about the composites now. Okay, composites and cryogenics. This video we have seen now. So what we have seen is the material created with the fiber reinforcement and a resin matrix material. The constituents retain their identities but act in total. So fiber generally refers to the filamentary materials. There are several types of fibers which are used. E-glass fibers, S-glass, Kevlar 49, alumina, carbon fibers of different types. Epoxy resin generally refers to a broad range of epichlorohydrin-based resins, catalysts, curing agents, and also additives. The polymer resins are mostly cured by either a heat or by a catalyst. They are also generally thermoset types. That means they're subject to temperature, it will get set faster. For specific cryogenic applications, the composite materials can meet the stringent requirements that metallic materials cannot. For other applications, the composite technology offers improved performance and lower costs. Okay, what are the advantages of the composite materials are? Lower thermal conductivity, high strength and stiffness, lightweight, usable down to 1.8 K, tailored structural efficiency, dimensional stability, close tolerance, improved insulation, corrosion resistance, minimum flaw propagation, etc. Well, there are so many advantages if you use them. Okay, but what are the disadvantages? First of all, there is a lack of standard composite material database. We don't know which one to choose, where to choose from. And secondly, the cost of these materials and the complex design parameters and manufacturing process. So these are the things which limit our work in this composites for cryogenics. Okay, let's move on to the fibers. Fibers provide the primary load carrying characteristics. I think you people are well aware of many of these things because many people are working on the composites. So this is just an introduction to those who do not know much about the composites. Several excellent fibers are available. Quantitative data at cryogenic temperatures are not available even now. If you take the tensile strength of a fiber, it increases when used at 83 Kelvin, or let's say liquid and close to liquid night temperatures. It goes down by almost, it improves by about 54% in the case of E glass, and it improves by about 80% in the case of S glass, started from their room temperature values. Okay, what about the costs? Cost wise, E glass is the lowest, S glass then follows S glass, then medium strength, low modulus carbon, then Kevlar 49, then high modulus carbon. The costliest is the alumina fibers. Okay. Other carbons are in the intermediate price range. Okay. I don't know how good is this this slide in front of you. It's not very clear, but anyway, this lists the properties of the fibers at 295K. We study here the E class, S class, Kevlar 49, alumina, and then carbon-based fibers. It's the data that is shown is tensile strength, tensile modulus, and then density. These are the parameters which are shown. And as I mentioned, you have various values for this. Okay, now let's come to resins. The resin binds the fibers in the proper position, distribute the load between the fibers, protects them from abrasion and environment, and provides interlaminar shear strength. The elongation to failure of most of the cured epoxies are quite low. Hence, they provide a good cryogenic performance, structural integrity, and also cost-wise, they could be minimal. Epoxies are found to be better than polyesters in resisting moisture and environmental conditions. Some two properties are shown, actually, mechanical properties, they are found to improve. For example, typical properties of thermoset resins are shown here. Again, I'm sorry for the quality of the slide. Amine cured epoxy or anhydride cured epoxy and vinyl ester. These are the three resins which are shown here. The properties shown are tensile strength, modulus, then flexural strength, shear modulus, etc. And then outgassing are the various parameters, like how much is the gas output from this outgassing parameters, etc. are shown here. Okay. These are all 295K at the room temperature. What about laminates? The cryogenic composites are typically fabricated by wet winding. Continuous fibers are embedded in resin, winding the pre-preg tape, laying up or forming the woven fabric, or injection molding thermoplastic resins containing discontinuous fibers. I think some of the things were shown in the video. You have seen that actually, how they fabricate. Okay. The fiber placement is followed by some temperature or pressure curing process. The mechanical properties of such materials are shown in tables or some references. The tensile strength and other mechanical properties are generally found to increase at low temperatures. Okay. Now, the typical properties of unidirectional composites at 290K is shown in this table. You have 60% by volume continuous fibers in the epoxy resin. So you have E glass, S glass, Kevlar, and then carbon-based fibers. And the properties are strength, modulus, the density, etc. All these informations are given here in this table. Now let us look at, for example, the thermal conductivity and maximum stress that these composites can take. The values are shown for 4 Kelvin, 77 Kelvin, and 295 Kelvin. I'm not going into any of this naming any of them. In general, what you see is room temperature has got a high thermal conductivity. As you keep going down in temperature, the thermal conductivity drops. Okay, the 4 Kelvin has generally the lowest thermal conductivity values. Okay, what about the stress, maximum stress it can take? Here, the number of cycles to failure is plotted here, and you can see here the values generally improve at the for different fibers. For example, epoxies, they generally perform fairly well at low temperatures, and you can see the number of cycles are fairly large for MSLM carbon epoxy based at 295K. I do not know whether we have a data at 4K. Yeah, there is a data at 4K. For example, S-glass epoxy at 4K is shown here. Okay, this is this one. And alumina epoxy at 295K is shown here. So most of the data is at 295K except for one of them, which is the S-glass epoxy, which is at 4 Kelvin. What you see from this figure is that this data indicates that the performance is better at lower temperatures. Okay. The cooling generally improves mechanical performance, but the data is very limited. The strength of G10CR increases by 100% and the modulus by 30% when you cool from 76 Kelvin to 4 Kelvin. The compressive strength also increases from 295 to 20K, in the range from 295 to 20K. For different glasses like this, for example, for 55% for S-glass, 27% for Kevlar 49, and 33% for carbon composites. The filament wound composite material strength increases at least by 30% when cooled from 295 Kelvin to 76. So what it shows is that when you operate the things at low temperature, the strength and the mechanical performance of these composites improves. Okay, what are the failure mechanisms? There are 4 basic fatigue failure mechanisms. One of them is layer cracking, delamination, fiber breakage, and the fiber matrix debonding. Okay. The fatigue strength depends on the basic materials, maybe the fiber orientation, composite quality, and the test specimen whatever configuration of the specimen what you are choosing. And then the higher modulus fiber generally provides better strength. And as I mentioned, fatigue performance also improves at cryogenic temperature. We have seen in one of the tables there earlier. How do you compare this with the metals? You can compare it by using ratio critical values. Low ratio of thermal conductivity to strength can improve the system performance and reduce the cost when the composites are subjected to large temperature gradients. So composites certainly have an advantage when you have a large temperature gradient in terms of thermal conductivity. High ratios of modulus to density, it will reduce the weight and hence the loads and hence increase the loads on the equipment. For example, E-class composites compare well with that of steel or aluminum. The strength to density ratio becomes at least twice for steel and almost 5 times for that of aluminum. What about the application areas? The application areas are many. I am listing out only a couple of them. For example, it's used as fuel tanks for liquid hydrogen instead of aluminum tanks. For example, we can think of people have used for the reusable launch vehicles, liquid hydrogen tanks of 5 mm thickness, 2.5 meter diameter, and 4.9 meter height, carbon epoxy type tanks. GR type composites are used for support and insulate the liquefied LNG tanks. They are also used as support in vacuum insulated LNG fuel tank of trucks, buses, and trains. Filament wound straps are used to provide structural supports, thermal isolation of cryostats and superconducting magnets. Composite straps are used in MRI, magnetic resonance imaging, and magnetic energy storage systems, also on space shuttle, Hubble spacecraft, cosmic ray background explorer, etc. Nested tubes allow use of glass composites between ambient and 76K and carbon composites below 76 Kelvin to optimize the thermal performance. Fermi National Lab, for their superconducting dipole magnets, they have used reentrant pores developed out of G10 CR nested support tubes. Now I'll show you a couple of photographs here to show the use of composites. For example, the one which is on the leftmost is a composite support strap, and the one below here is the liquid hydrogen tank on your extreme left, but down below. Then next, nested composite tube with heat intercepts are shown in this one, in this photo. The right hand side shows you, for example, the tubes, neck tubes, which are used in cryostats. Okay, you can have a different type of neck tubes based on, these are the FRP tubes which are used. They are also used in helium vessels for intercepting the heat content of the outgoing helium vapor. It is inside the helium tank itself. The one on the rightmost bottom is the composite neck tube with stiffening rings, which are used as neck tubes for special applications. Okay. I think I have come to the end of my talk. There are a lot of sources of data on cryogenic properties and material available. A reference guide of cryogenic properties by Wiesent, Flynn, Thompson, etc. Then there is a cryogenic material data handbook is available by Durham et al. There are some computer codes generated which are called Metal Pack and Cryocomp, and they are also available. So if you want to calculate directly what should be the length of the neck tube or what should be the thickness of the shell and things like that, it can be used. And there are also information available in the proceedings of the International Cryogenic Material Conferences. Well, for the composites, I do not have much data because I am not a composite man. So I think I have come to the end of my talk. I thank you very much for your patient listening. And in fact, I hope whatever I presented will be useful to you. I would like to also mention, if you want to ask me some questions, please ask me, not in the area of composites, because I do not know much about that. Okay. Thank you very much once again. And for the opportunity, I thank the organizers for their excellent arrangements. I hope this presentation will be useful to you at some time or the other. Have a nice day. Thank you. Hello. 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 Yeah, you are audible now. My presentation is complete now, right? Yeah. Yes. Okay. I presume that when you talk about safety, you are talking about the cryogenic safety. Okay. Now, the cryogenic safety is generally, it's actually, people have to adhere to wearing the gloves and goggles when you use cryogenic fluids. Okay. And many a times, if you are, you also have to have ventilated rooms so that the nitrogen content in the room does not cross beyond a certain point, so that asphyxiation cannot take place. So these are some of the things which you normally do. Okay. So handling of cryogenic fluids should not be done by bare hands, etc. Okay. One more thing is, in case by accident, if a cryogenic fluid falls on your hand or some parts of your body, immediately wash it with water so that you bring it back to room temperature immediately. Okay, actually what happens when a cryogenic fluid falls on your body, it extracts heat. It's almost very similar to a hot water falling on your body, which gives you heat. The effects are the same. There also you will get bubbles. Here also you will get bubbles. Okay, after the thing is warmed up to room temperature. Okay, and normally you can apply ointment like Bernal and so on after it is warmed to your hand is warmed to room temperature. Okay, now this is as far as the cryogenic fluids are concerned. Ensure always, if you are using a cryogenic tank, it is not fully closed. Okay, or safeties are properly functional. Okay. Now coming to cryogenic cylinders, big, for example, storage of gas, etc. These cylinders have to be regularly tested. They perform what is called the hydrostatic testing, and this testing has to be done at regular intervals and make sure that cylinders are usable at all times. Because what happens is when you are using let's say a high pressure gas in the cylinders, because of the continuous usage, there will be slight expansions that will be taking place, and the hydrostatic testing will ensure that these expansions are within the limits. Okay, I think I have covered most of the safety things which are there as far as the cryogenic. Preferably in many of the occasions, it is preferable to have another person working with you in the lab. In case of any safety problems, the other person can help you out. Okay. Yes. See, I'm not a doctor. Because of that, I may not be able to directly answer this question. But what I know is, for example, people have used for Parkinson's disease. Okay, there are some needles which are inserted into the brain, wherein the cryogenic fluids can enter, and thereby it can be used to cure. I don't know what exactly is the sort of things that are done by a doctor, but as far as I know, Parkinson's disease people have been able to use the cryogenic fluid, or at least the cool down by cryogenic temperatures. Okay. Now, of course, there are some videos which are available which shows that, for example, when you have an operation done on an open heart surgery, an operation done on a patient, which loses a lot of blood. People have used cryogenic fluids like nitrogen to be circulated through a bed, through a heat transfer bed, which is mounted on the patient's body, such that the blood is frozen at all the other places except the zone where the operation is being done. So there are some old videos out there, but I do not have any of them here. Okay. As I mentioned yesterday, ocular lenses, the eye lenses, can be lifted out by using a cryo probe or cryo tip, okay, cooled to a certain temperature. Okay, this is possible by using that. And then dermatologists use cryogenic fluids for treatment of warts. Okay, but that is warts are unwanted growths on your parts of the